Okay, so we have a pendulum. And I'm going to kind of exaggerate. Now these are not at equal intervals because the pendulum is not moving with consistent velocity, right? Okay. So I'm going to color code some quantities. I'm going to hold them in chalk. So I'm going to draw these again. You know, it's this kind of picture, but I'm going to draw them further apart. Okay, in the middle ones where the string is hanging straight down, and I'm not going to draw the string and all the, well, you know, I might as well. Might want to depict the tension and stuff. Okay, so we're out here. Now this is not really showing an arc. It's like the thing is running flat because I'm kind of exaggerating the scales. You know, it should be more, you know, circular arc with the center up here if that's where it is. We kind of imagine that really this point is, you know, 10 feet above us. So the thing is, you know, the arc is almost a straight line. Okay. Now, when we're here, we have tension. And I'm going to draw the tension for every one of these. Somehow I didn't manage to hit the center of the circle there, but you understand what it's supposed to be. And these are all supposed to be the same length. I'm probably off by 10% plus or minus from the average, but you know, you can see they all look like they're about the same length. So, okay, these are the tension vectors. And then and I'm not going to draw the entire triangle except for the first one, but the tension in the x direction is this. Okay, we just project this vector down to here, and here there's no tension, and here now tension's going in the opposite direction. So that should make pretty good sense in terms of some of the pictures we've looked at already. Okay? And really the tensions are not exactly equal. But again, if the fulcrum or the point of attachment is up 10 feet, even 10 meters, it's very nearly constant. Okay? Okay, so what happens is you have a tension that keeps, you know, a component of the tension that keeps decreasing. Now, I haven't drawn the gravitational force, I haven't drawn the vertical component of the tension. They're presumably, at least in our approximation, equal and opposite, so they don't contribute anything. Okay? And we've seen that picture. I think I asked you to do something with that picture. So we have, as a result, an acceleration at this point, this point, this point, this point, right? I could draw the acceleration vectors equal to the tension vectors because acceleration is a different quantity. It's going to be graphed, it's going to be represented on a different scale. Okay, your acceleration in SI units is going to be meters per second squared, whereas your tension is in newtons. And I haven't even defined what a newton is. Okay, I'll probably do that off to the side in a minute. Okay, anyhow, these are your accelerations, and I'm choosing to draw the acceleration vectors a little bit bigger than the tension vectors. Okay? So every acceleration vector maybe is 25% longer than the corresponding tension component. Okay? The component of the tension in the x direction. So these are accelerations. And they're vector quantities, accelerations in this direction. Now, what's happening to the velocity of the pendulum? Because this is where we really have to start thinking a little bit.
It's changing.
Okay. Now, what's the velocity here? Well, presumably, these are the extreme positions of the pendulum. So how fast is it moving when it's at this position? 0, it stops. Okay, so we have just a dot there indicating no velocity, right? Now, when it gets here, it has some velocity. Okay? And I'll choose to draw the velocity vector maybe about this long. Okay? So the change in velocity between here and here this is velocity. So between here and here, we have a delta V. This is as long as this vector. Now these vectors have to be to the same scale because they're both measuring units of velocity, right? Okay, so from 0 up to this, the change is just this. Okay? Now, how much change in velocity do we expect to get between here and here? Is it going to be this much, more, or less?
Less.
Why less?
Because the acceleration vector is smaller.
I'm sorry, I can't hear you over the class next door.
Because the acceleration vector is smaller.
Yeah, the acceleration is less. There's less force, so there's less acceleration. So it doesn't pick up as much speed. Okay? Okay, so we're going to draw the delta V vector first. And if the delta V vector is this long, when the acceleration is something between this and this, right? Because the acceleration is changing. But when the V vector is this long, the acceleration is somewhere between this length and this length. Now the acceleration is somewhere between this length and this length. It looks like it's maybe, maybe just a little more than half as much as this. And you can make your own judgment. Of course, it can be calculated. That's easy. But you want to get the picture and you want to understand what's going on. So I'm going to draw a change in velocity vector that's maybe close to half that, maybe a little more, maybe a little less than half. Okay? So how long is the next purple vector going to be?
As long as the last one was plus the change in V.
Yeah. It's going to be the length of this one plus the length of this one. So I'm just going to attempt to do that. Okay, and I'll put a little mark here for where this one ended. That's about how long this one was, and this is about how long this one is. Don't think I did that very accurately, but it's okay. Okay? Now what's the change in velocity going to be next time?
There won't be one.
I'm sorry?
It won't change, will there?
Well, it will, because at this point you do have an acceleration. Now by the time you get to this point you don't, but an average acceleration over here is going to be something between this and this. It's not going to be the average of these two, the numerical average, because it's not changing linearly. And you want to maybe ponder that idea. But so we're going to have a pretty small change in velocity here between here and here, which will give us a velocity at this point. It's not much greater than the one we just drew. Okay? Okay, so now what's going to be the change? Actually, that's probably shorter than the one I just drew. I don't want to get it too long. I anticipated my scale. I didn't do a very good job of it. Okay, so it's a little longer. So that's this long, we'll make it just a little longer. Okay, that looks like it's a little bit longer. Okay? Okay, now what next? What's the change in velocity vector going to look like?
Be negative.
Yeah, it's going to be an average, not an average of this and this, but something between this and this. It's going to be now in this direction, and it's going to be equal and opposite to this, because your restoring force is the force negative is of the your restoring force is a negative, constant negative multiple of your position relative to equilibrium. So if this points as far to the right as this is to the left, and it looks like it kind of is, because these are kind of equally spaced, then this is going to be equal and opposite to this. As length appears to be about equal and opposite. I drew the arrow at the end of the vector, the head of the vector a little too long. But so this one's going to become less. And if you think about it, it's actually going to be as long as this one. Because to get this one, we added this to this, and now we're going to subtract this from this, but this is just equal, and we're going to add this to this, but this is equal and opposite to this. So we're going to end up with this, which should be equal to this, right? And then we're going to have a somewhat greater change in velocity, but of course it'll be negative, meaning that we're going to slow down, and by the symmetry of this whole thing, by the fact that the restoring force has a symmetry with respect to this direction, this vector has to be the same as this one, right? And then when we get out here, well, our change in velocity is going to be the same as this one, but opposite in direction. Better to say it's going to be equal and opposite to this one, okay? So these delta V vectors are symmetric. Okay? By reflection, something you hopefully had emphasized in pre-calculus, so it's a familiar notion, but it's not a difficult notion. You understand if we reflect this picture through a mirror here, we get this picture. Okay? So, we can say that this plus this equals this, right? Understand what the plus and equal mean? This, I've got a little line running from here to here, and then a little line running from here to here. So, if I, and I don't want to put an arrow on it because it'll look like a vector then. But this plus this equals this, and this plus this equals this, etc. Right? Okay? So now, what I'm going to ask you to do is sketch a graph of A versus X and V versus X.